Hello, welcome to the Journal Computing Information Science and Engineering JCISE monthly Spotlight Talk. Today is my pleasure to introduce Professor Panchal from Purdue University. Professor JCISE Panchal is a professor of mechanical engineering, School of Mechanical Engineering, as well as associate chair of undergraduate study in the school. And JCISE has award won the numerous awards in the engineering design, especially. I won't probably go through all these awards, including NSF and so on. And for today, and like to have the opportunity to see the latest work Professor Panchal, his group, and working on, and cybersecurity in manufacturing, and beyond this, cybersecurity in design manufacturing, Professor Panchal also has been working on engineering design and this cyber physical social system, especially in recent years, and very exciting work, and have been learning in those past years from Jatish. And okay, so and then without further ado, and let's pass on the time and to Professor Panchal and Jatish, please take over.
Thank you so much, Professor Wang, for this introduction. And thank you so much for inviting us to give the spotlight talk for JSISE. So this work is focused on trying to bring in some of the security concerns within the design and manufacturing process. Specifically, we are looking at how information can be embedded within parts through the manufacturing processes. This work is primarily, the lead author for this is Karim El Said, who is a PhD student in mechanical engineering at Purdue University. So just to motivate this work, there is a big problem of counterfeiting of not just electronic parts, but also of mechanical components. So for example, there have been various instances where counterfeit fasteners have been used in aerospace systems, for example, helicopters, and that has led to several crashes. Similarly, in the automotive industry, billions of dollars are lost in counterfeit parts, and there is a need for developing approaches and technologies to prevent such counterfeiting. And there have been a number of different ways in which this problem of counterfeiting has been addressed. One approach is to use policy tools, for example, coming up with new laws, penalties against any counterfeiters, so that can discourage manufacturers from producing counterfeit parts. There have been a number of standards in this area. But then the other approach for addressing this problem is more technological. For example, there is this notion of physically unclonable functions, which is functions that cannot be replicated or remanufactured even if we wanted to. So even if we knew exactly what the microstructure of the part is, it is extremely hard to replicate that microstructure exactly as it is. So such an approach can be used to address this problem of counterfeiting. Specifically, we focus on additive manufactured parts. And recently there has been a lot of work to understand security in the context of additive manufacturing. There are a number of different concerns, for example, piracy of CAD files, piracy of process plans. There are issues with sabotage, and of course, we talked about counterfeiting. And there is a existing literature on a complete taxonomy of the kinds of different attacks that are possible within the additive manufacturing domain. So our work fits within this literature. Specifically, we focus on two areas. One is watermarking, which is where we add some sort of information inside the part. For example, in the case of images, we can watermark JPEG files. In terms of audio, we can watermark audio files. And second is fingerprinting. And these two are related approaches for addressing counterfeiting. So the idea of embedding information or hiding information in objects is not new. This is something that has been researched a lot within the digital artifact community. For example, audio watermarking is very common when you purchase MP3 files, for example, from Apple Store or any other online store. Similarly, watermarking of images is a very well-established technologies, and we can embed signatures within images. Similarly, there is work on embedding watermarks in text also. So there are ways in which you can embed information within, let's say, a page of text, so that we can identify whether this is coming from the original source or not. And recently, there is similar work on embedding information within CAD files also. There have been some efforts at adding signatures or watermarks within 3D printed parts. For example, uh, one of the earlier works here on the left-hand side embedded information on a 3D printed part on their surface in terms of some random surface patterns, let's say some bumps, some depressions in the part, and those could be then read by an optical scanner to identify what information is embedded in the part. Similarly, there are other approaches where we can embed QR codes or barcodes in terms of different materials within the part. There are other techniques where we can embed codes inside the part so that it can, and these codes are not directly visible from outside, but through techniques such as scanning, or through some audio-based techniques, we can actually identify which specific code has been embedded in the part. So along these lines, our approach is try to use manufacturing process to embed such information within parts. Now, some of the key challenges in the existing approaches that I just showed on the previous slides is when you modify the structure of the part inside it, it also affects the properties of the parts. So we want to make sure that whatever information is being embedded does not really affect the functionality of the part. And second, we want to make sure that when we are embedding this information, we don't require any modifications or any extra steps in the manufacturing process. So considering these two objectives, our primary task here in this particular paper is to define an efficient and reliable scheme for embedding information, and trying to figure out how do we maximize the amount of information that can be embedded inside the part. And this maximization of the information content is, we refer to as the information capacity of the part, while considering the process capabilities that we have and how the part is going to be used in the real usage. So our proposed approach in this particular paper is to use manufacturing process control, particularly additive manufacturing process control, to achieve information embedding. We view information embedding problem as a noisy channel coding problem, similar to how it is used within the information theory, where we think about a part as a carrier of information. And when the information is embedded, the information is embedded when the part is manufactured, and we will read that information later on, maybe after it has been manufactured or after the part has been used for certain time. So we think about this part as the CAD or as the channel which is carrying that information. And when we embed some information here, let's call it M or a message M, we want to read that message, and that message may get modified during the manufacturing process or during its usage. So we want to try to maximize the probability that we are going to be able to read the same information that was embodied earlier on, because there may be a number of different effects within the usage that may modify that information. And then finally, we want to come up with computational design techniques to optimize the amount of information that the part can carry. So our proposed approach is to start out with a CAD file and then decide what information we want to embed. Specifically here, we look at embedding information on the surface of the part in the form of either barcodes or in the form of 2D QR codes. That information is then coupled with the manufacturing process plan, for example, a G code, to update the G code in a certain way, and I'll discuss how we achieve that. That updated G code is then sent to the additive manufacturing equipment, and then we print the part. Now, this part of going from the CAD file and adding that information is referred to as the information encoding step. And then once the part has certain signature embedded in that, then we go to the decoding step, which could use either optical scanners or profilometers or any different type, many different types of ways in which we can read the information that has been embedded in that part. And here we show how we can use image analysis to extract the message and what are the different sources of uncertainty that come up in the entire process, and how do we account for that uncertainty in order to figure out the maximum information content of the part. Now, if we are able to put some information in the encoding step, and we are exactly able to identify the same information in the decoding step, then there is no error in the entire process. Then the information capacity, let's say, is 1, which means I put in a bit, let's say 0 or 1, and I receive the same bit 0 or 1 out from there. However, if there are any errors in the manufacturing process, or if there are any errors because in the decoding process, that bit 0 may be read as 1, or a bit 1 may be read as 0. And this error may reduce the capacity that we can have in that part. So we want to quantify what that information capacity is. So specifically in this paper, we use the speed of the head as a way of embedding information. So if you look at this example part here at the bottom, there are two different types of features that you would notice. One is the shiny blue colored, and the other is some rough surface. We achieve these kinds of patterns by speeding up the head in certain parts of the printing process and then slowing it down in the other parts. When we are speeding up, we get one type of a feature, and when we are slowing it down, we get another type of a feature. And these two phases, we refer to them as bit 0 and 1. And that's how we achieve this information embedding of the bits of 0 and 1. And our approach, again, here is using speedhead. Now, there are various other ways in which we can achieve different types of signatures. For example, in some of the prior work, we have used vibration motors, where we activate the vibration motors that are attached to the frame at certain points in the printing process, and that includes certain types of signatures. So there are many different ways in which we can achieve different features and embed information. So in this particular paper, we focus on the speed as the variable. So this is just another depiction of how or where that information is getting embedded. So this on the right-hand side is the surface of the part that is getting printed. And when we slow the machine down, we get this larger bead size. For example, this is a figure that shows the effect of speed on the size of the bead. So for example, when we slow it down, we get this bit 1. But when we speed up the head, then we get this bit 0, which you can see in these experimental results. And that gives the surface a specific signature with the information that is embedded. So our information encoding scheme consists of 5 steps. First is to generate the message. Now, this message can be just some sort of a binary string, or it can be any other type of if we come up with a different types of an alphabet, for example, hexadecimal, then we could come up with different ways in which you can embed information. But here in this paper, we only focus on binary strings. And we focus on generating these randomly because we want to be able to embed any information that the designer would like to add to the part. Then using this, we determine what the encoding parameter should be, which means what should be the speed of the head to which corresponds to the bit 0, and what should be the speed of the head which corresponds to bit 1. And we come up with the optimum combination of these two speeds, along with the width of each bit. So now in this previous slide, for example, here, we have this as the bit width. So as you can see, that's the width that we're using to quantify a certain 0 or a 1, but that can be changed. We can have a smaller bit width or larger bit width. If we have a smaller bit width, then we'll have more information in the part, but if we have a wider bit width, then we'll be able to encode less information. But the advantage is that the probability of reading that bit would be higher. So once we choose the encoding parameters, the next step is to map that code to be embedded across different layers, and then modify the outer layer speeds for the G code, and then print the part. Here is one example of the kind of a part that we could print. So as you can see, in this particular surface, we have three different regions, one on the left-hand side, one in the middle, and one on the right-hand side. And there are different layers, as you can see, which have these different protrusions. So that part is printed corresponding to this matrix of bits that have been produced. For example, this dark color is 0, this is 1, this is 0, this is 1, and so on. And we can use optical profilometer to measure the height at each point. And this is a depiction of the kind of height profile as we cut across this vertical lines here. And we can use that to determine whether a particular point corresponds to bit 1 or bit 0. And that's how we're using, extracting the information that has been embedded. So this is just as an illustrative part just to assess the impact of different speeds. And then in terms of the decoding process, again, as I said, we could use different ways. We have used a simple paper 2D scanner. We have used a camera on a cell phone. We have also used an optical profilometer to assess the impacts of different reading techniques. Clearly, different reading techniques will have different levels of error associated with them, and that affects how much information we can embed. So the steps in the decoding process is we start with the part, we scan it, and then we perform some image processing techniques such as noise removal, thresholding, and then we classify each point in the surface as either 0 or 1, or a misclassified bit where we are not able to decide whether it's 0 or 1. And that is what is used to calculate how much error we have in the overall part. To come up with the optimum values of the two speeds, we use design of experiments in terms of the different differences in the speed. So what really matters is not the absolute values of the two speeds for 0 and 1, but the difference between the two speeds. The higher the difference, the more likely we are able to characterize the bit accurately. And the lower the difference, the lower will be the difference in the surface profile for the two regions, and then the higher the error in that. And then on the y-axis here, we also experimented with different bit widths. And what we found was that the difference in speed has a much higher impact on the classification accuracy compared to bit width. So we focus on using the best value of delta S in order to make the decision. So then once we come up with the optimum values of the two speeds, then we start embedding 2D signatures like the QR code. So here is one example of a QR code that was printed on the surface of this plastic part. And as you can see here, we are using a 2 by 2 millimeter region as 1 bit. And this corresponds to 1 bit. And we are classifying this region as either a 0 or a 1. And that corresponds to this region in this particular part. So this would be 1 bit, this would be another bit, this would be another bit, and so on. And we are using that to then assess whether we can read this QR code accurately or not. Now, clearly, we can have different sizes of QR codes with different error, resistance. And here, we are mainly trying to assess what should be the minimum size of this bit, what should be the minimum difference in the speed, so that we can have a good part, but with reasonable accuracy, with which we are able to assess whether the bit is 0 or 1. Now, in terms of classification, so once we read the image and then we are trying to classify each region as a bit 0 or 1, we have used several different types of machine learning techniques, ranging from logistic regression to SVM to random forest to CNNs, convolutional neural networks. And what we found was that in this case, the convolutional neural networks had the highest accuracy. So in this case, we were able to have an accuracy of about 98% in the parts that we tested. And one thing that I would like to highlight is when we're training the CNN, we are not training it for the entire QR code, because that would require a lot of different prints to train the CNN, but instead we are training it a bit at a time. So we are training the CNN for smaller regions, like this is a region that was shown earlier. So each image or each part that is printed with a single QR code will give us a lot of training data, like 400 or so images directly that can be used to train. So that reduces the number of parts that we have to print in order to train this CNN. So we go with the CNN as our classification method. And then the next question that comes up is, what is the maximum amount of information that we can embed in this particular part, given that we have fixed our speed, given that we have fixed our uh, way of estimating the bits, like we have fixed CNN as the method for estimating. And that's where we again go back to information theory and using the Shannon's theorem and quantifying the channel capacity. So the channel capacity is basically the maximum amount of information that can be embedded using a particular channel, where we are putting in some information X and we are reading out some other information X hat. So we use that as our objective function and try to maximize that measure of information capacity in the channel. Now, there are various different types of channels, and the channel that we model this as is the binary asymmetric channel. So in a binary asymmetric channel, you're basically sending a binary signal. It's a 0 or a 1 at a time. And then that 0 may be read as a 0, or it may be read as 1. So when you're sending a 0, it may come out as 1, and that's the error. So that error is the error in bit 0. We represent that as epsilon 0. And similarly, if you're sending a 1 and then we are receiving a 0, that's the error in bit 1. We represent that as epsilon 1. Now, these errors may be equal. In that case, it's a binary symmetric channel, but these errors may be different. So in this particular case, we found that our error rates were actually different when we are sending a 0 versus sending a 1. So we use this BAC, which is the binary asymmetric channel, and that can be used to then calculate the capacity of the binary asymmetric channel. So this is the formula using entropy. And what we see here is a plot that shows the information capacity as a function of the two errors. So if epsilon 0 is the error in 0, epsilon 1 is the error in 1. And what we see is the 3 points that are shown here correspond to the different differences in the speeds for the 2 bits. So if this difference in the speed is 10 for bit 0 and 1, then we notice that the error corresponding to 0 is about 0.8, and the error corresponding to 1 is about 0.35 or so. Similarly, if the difference is very high between the 2 speeds, then we find that the errors are low. Epsilon 0 is close to 0.4 and epsilon 1 is close to 0.1. So so using that information, we want to figure out, okay, what should be the parameters that we can control as designers and manufacturers to maximize the information that we can embed. So the optimization that we are doing here is to maximize BAC. And the 3 variables that we have for maximization are, one is x1, which is the speed for bit 0, x2, which is the speed for bit 1, and x3, which is the width of the bit. Again, the lower the bit width, the more information you can pack in the same region, but higher the possibility of error is. Okay, what we found was that in this optimization problem, we can actually decouple the 2 optimization problems, one for x1 and x2, and the other one was for x3, which is the bit width. So we can do these 2 optimizations independently. And for this optimization, we use the sequential Bayesian optimization techniques that have been very popular in the design literature. So we start out with a set of points. We use those points to then fit a response surface. And then we pick the next point based on where we can maximize the improvement in the objective function. So So using that, after 20 iterations, what we found was that the optimum value of x1, which is the speed for bit 0, and the optimum value of x2, which is the speed for bit 1, are somewhere in this region. And since it's a symmetric problem, both of these regions are converging to the optimum value. So speed 1 is close to about 12 or so, and then speed for x2 is about 42 or so. So this is the optimum design of these parameters. S0 is 12 and S1 is 42, and we use that to print the part just to show what kinds of differences in the features you can see. So as you can see here, we are clearly able to see the differences between bits that correspond to 0 and 1 here, for example, right here. Versus if S0 is 9 and S1 is 21, here it is a little bit harder to figure out which region corresponds to bit 0 and which region corresponds to bit 1. So in fact, the average accuracy for this is 0.97. And if you go to S0 of 6 and S1 of 25, the average accuracy is lower, which is 0.93. So this is just to compare and show the effects of the differences in the speed. Now, if surface finish is an important factor, then maybe this design would actually be better, but only from the perspective, if you're only looking at one objective of maximizing the information embedding capacity, then this set of parameters are the best. So again, this shows the trade-off between surface quality and the information embedding capacity. Now here, in this particular case, the information capacity comes out to be 1, which means that every time we read this, we are able to accurately assess each of those regions as being 0 or 1 accurately. Okay, so now, as I said, so far we have only looked at optimizing for the information embedding capacity. We haven't really incorporated the functional characteristics or the objective for which the part is being designed. So for example, we haven't really looked at surface roughness. We haven't really looked at strength of the part or what impact this could have on fatigue properties, for example. So our current work is focused on trying to look at these multiple objectives, saying, okay, what if we are trying to maximize stiffness or minimize compliance, while at the same time trying to embed information in the part? Can I come up with an object optimization problem where we maximize information capacity while also minimizing compliance? So here, in this particular study, which is a follow-on of the previous paper, is focused on trying to address that multi-objective optimization problem. And here, as you can see, this is the standard cantilevered beam design problem from any topology optimization paper that you can see. And here we are trying to say, okay, what if I wanted to embed a 2D QR code or any other code in this part? Where should I place that code? And what is the maximum size of that code that could be placed so that I can achieve both of these objective functions? So here, this is just a very quick snapshot of the trade-off between information content, which is the size of the code that we're embedding. So as you can see from left to right, we're increasing the size of this 2D code from 9 by 9 matrix to 441 by 441 matrix. And then the optimum stiffness that could be achieved as we are trying to do the topology optimization with the constraint of that code as part of that. And clearly there is operator frontier that we achieve. And the main message here is, in addition to embedding information, there is a need to bring in the physical properties and the functionality of the part. And there is always trade-off between the two that needs to be taken into account. And with that, I finish the quick overview of this particular paper. Here are some references that are related to the work that we are doing in this direction of embedding information in physical parts. So Jan, back to you.
Thank you very much, Professor Panchal, and also co-author Karen, for excellent work and very nice presentation.
Thank you.